Hey, what's up? Nathan here from PH Studios. This is going to be a very complex tutorial, and it's going to be one of the first ones from the Tower Defense series. It's not really from the series, but it's going to be a requisite or a sort of demonstration of the algorithm we will have to use in the Tower Defense series. So I'm going to label this as a Tower Defense tutorial, since we will be using the algorithm with minor tweaks and things, but this is the core of the AStar algorithm. Alright, so the tower defense tutorial will contain 3 levels. One of it will be like a forest type level, another one will be a snow type level, and the third one will be a unlimited or lifetime or forever. Yeah, endless, that's the word. It's going to be an endless map. So the way the endless map is going to be is we're going to have a spawn location and a destination location. Now the spawn location and the destination location, in between that we'll have a giant open area that you can put your towers on. And then we will have to determine a path that the monsters or whatever we decide can travel between the spawn to the destination the most efficient way possible. So that's what we will be using. We'll be using a pathfinding algorithm known as AStar, and I'll explain what that does shortly. The forest and the snow, they will not be AStar. They will not be an endless maps. They will just be a designated path that the monster or enemy will have to travel to get through. The only one that will do this is the endless one. Okay, so before I walk you through the completed sample, I'm going to actually talk about the algorithm. And I'm going to try another video overlay because it will get very complex. So watch the video and try to follow with me. Alright, so for an example, let's take a 4x4 map, a 4x4 grid, and we have a start location somewhere and an end location somewhere else. Now we want to find the shortest path from start to end. Now the way the algorithm works, and when I first did this, the tutorial was supposed to be out a week ago. The way I was doing it, I was trying to find a very easy way to do this. I was doing about half the work with one important step missing. Now I'll walk you through the whole algorithm and I'll mention the parts that I am missing. Okay, the two of the most important parts that I had missing was, one of them had to be, you have to have lists. You have to have an open list and a closed list. Now, getting away from the video overlay, if you see on this completed sample, the red tiles are on the closed list. Nothing is being displayed that's on the open list. If you visited a node on the open list and then changed it, it's now on the closed list. So every node we touched is either on the closed list or in the path. Alright, back to the video overlay. Okay, so it's taken me over an hour and a half to even do 2 nodes on the video overlay. I was trying to make it so you could watch the video as it walked through, but I'm not going to spend 6 hours on that one video. I might later this week, but for now I think I'll have to do this the very poor way, which is just go over a picture I did. And I mentioned I did this a lot on paper, so this is one of the papers that I did. Okay, so we always start with the starting node. That is always going to be the starting node that we need to have. The way it's set up is we have the 3 terminating states, so as long as we add the starting node in there, the open list should not reach 0, unless, of course, we cannot travel to that end node. So we set the starting node. We have that selected. That's our selecting node. Once we do that, we need to drop it from the open list and then to the closed list. So that's the first step. Now we want to see if every adjacent node, and what we want to do here is if it's not already in the open list, we add it to it. So here I'm going to add this to the open list. Now I also do my heuristics, and this is my optimized version like I talked about. So instead of getting the distance from start, for example, 8 and 7. This is the distance between here and here. So I'm only getting the distance between the parent and itself. But I'll walk you through that later. Alright, you can see what I did here. You can see the L1, L2, L3, L4, L5, L6, 7, 8, 9, 10, 11, 12, 13, and there we go. So you can see the L crossed, and that's what I did with the lowest. So lowest 0 is what we have first. Now, all the adjacent nodes, these three. This one, this one, this one. Gather heuristics. The heuristics are from here to the end node. So, what we have here is 1, 2, 3, 4, 5, 6. So 6 in the delta x direction. So we square the change in x, and that gives us the 36 you see here. Now, between here and here, we have 1 and 2. So 2 in the delta y, so we square the change of y, and then we get the 4 here. We add those together, that's how we get our 40. Distance from the parent, which is from here to here, it's just 1 in the x. We square 1, it's just 1. So now our total is 41. Now we do the same thing. 9 and 36. We have 1, 2, 3, 4, 5, 6 in the x direction. Square that, that's 36. So that's this here. Then we have 1, 2, 3 in the y direction. Square that, that's how we get our 9 here. Add them together, we get 45. Distance from start, that's 1, 2. So that's how we get our 2. Add those all together, we get 47. Now we do the same thing with this one, we get 59. That's it. Next loop through, we need to choose the lowest one, which is this one. That's why this is L1. Now we check to see if our adjacent nodes are already added to the list. They are already added to the list, so let's check to see if our new distance is better than our old one. So what our new one does is it takes this value, the distance from start, this value here, that 1, and calculates the distance from this node to the current adjacent node. Let's say we're looking at this one. So from here to here, that's 1. So 1 plus 1, that's 2. It's not better. From here to here, that's 1, 2. 2 plus 1, that's 3. So that's not better. So we do not change any of our parents. I don't think we change any of our parents in this whole example. So what we do here after that is these two are done. So the only two left on the open list are these two. Now we choose the lowest one, which is 47. So this one is the lowest one. Now we check to see if any of the adjacent ones are already added to the list, and this one is the only one. 2 plus 1 is not better than 1. So we do not update the new distance. These 3 have not been added to the list. So you see the parents' arrows are here. So this node's parent is this. This node's parent is this. This node's parent is this. So we update the parents with the current selected one, which is this because it's L2, and then we do our heuristics again. So now the only ones that are left are these and this one. So which one has the lowest? This one. This is why it has L3. Likewise, we add all these to the open list and this one to the open list. Set the parents, so this one's parent is this one. These three parents are this one. Calculate the heuristics again, and we're done. We do not update any of the other ones, so we're done. Now, we need to choose the lowest one from these three, these two, and these two, which is this one, which is 31. So that's why that's L4. Now, I did this on paper, so I ignored this one, because I was going to implement a way to calculate if it's surrounded by walls, do not allow the diagonal one here. Okay, just imagine that this one is a black box. Alright, so that's stuck. That's nothing. We do not have any adjacent nodes to test. We do not have any adjacent nodes to add, so that's it. What's the second lowest one? It's this one, 37. That's why that's L5. So I think you get the idea now. The only one that is not added yet is this one. So we set this one's parent to this one. This one's parent is this one. And now will be a perfect time to demonstrate it. The previous parent is here, or this is the distance from the previous parent node to itself. So 4 is right here. And then what's the distance between here and here? It's 1. So 4 plus 1 is 5. Okay, so now we have this one. This one's parent is this one. So we have 5 here, and what's the distance between here and here? It's 1, 2. So 5 plus 2 is 7. So that's my optimized version. I'm not doing like 100 distance between here and here. I'm actually saying the distance between here and here, plus whatever that value was. Okay, so I think you get the idea now. Now, once we calculate all that, we got our parents set up. Remember, we have to keep an eye on these arrows, our parents, because once we get all these figured out, and once we look at the end here, we need to go all the way back. We need to say, all right, from the end's parent, this is in the path. All right, now we go to the end's parent. This is in the path. Parent, this is in the path. Parent, this is in the path. Parent, it's pointed here. This is in the path. Parent, it's pointed here. This is in the path. 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 And this is in the path. Okay, I hope that's another a better explanation as well. And I'm not going to edit the video that well, so if I say, alright, back to the video overlay or watch the video overlay, just ignore it, because it's going to take me forever to get one done. I'm going to put this in the middle when I first reference this, and yeah, so there you go. I hope this is another explanation that will get you through it. So, we need to find the distance between point A, the start, and point B, the end. And we need to find the shortest path. So, we have an open list and a closed list. So, before we get into the algorithm, the open list must contain something. There's 3 termination states. Let me bring up my code here while you're looking at the video. Just 1 second here. I'll look in my map folder. Alright, there's 3 states that the algorithm will terminate. If the current selected node is the end node, that means we have reached our end node, we stop, we found our path. The second one is the open list is not 0. We do not have any more open nodes to visit, so we don't have a valid path, so we're done. The next one, the last one, is if the end dot parent is equal to null, is not equal to null. If the parent is not equal to null, we have found our path. So that was probably the most important thing that I missed in the first run through on this AStar pathfinding, is I did not implement the parents. Because the way the AStar works is you find the entire path. You look at all the nodes. Once you do that, you have to go backwards from the end, and then you say, okay, I got the end that's in the path. Now I got to add the next one to the path, which is the end.parent. Okay, end.parent's parent is also in the path. End.parent's parent's parent is in the path, and so on. So this will all be explained in the video. I'm just going over a brief overview on the termination states. Okay, so the very first thing we need to do, the reason why I talked about this is because the open list has to contain something, otherwise we know that the AStar did not find a path. Okay, so before we get into our algorithm, we have to add a single node to the open list. Well, what do we know for sure? We know our monsters will start at the starting node, so we will just add the start node to the open list. Okay, so now we added to the open list. Now we got to get into a while loop or some sort of loop that will do this until we reach those 3 terminated states. Alright, so while in the loop, we gather the lowest best node from the open list. Right now, it's just the start node. Once we do that, if that node equals the end node, we're done. We can finish. We're done. The node we selected is the ended node, so we already found our path. If it is not equal to the ended node, we have to remove that selected node from the open list and add it to the closed list. So any node we visit will be added to the closed list. Now, for every adjacent tile in that node's adjacency list, we need to do 3 different things depending on the situation. So the very first thing is if the adjacent type is not passable or it's already in the closed list, we do nothing to it. That means we cannot pass through it, and it's already in the closed list. We already visited it. So we do not need to do anything to that adjacent node. The second one is if that node is not in the open list, we need to add it to the open list, and then I set the adjacent parent to the current selected node. Now, when we add it to the open list, we need to perform the calculations for the AStar heuristics. So let me explain what that means. When AStar, when we're determining the path, it uses heuristics to determine the shortest path. Not just any path, but the shortest path. And depending on how well you do the heuristics, if you do it properly, it should guarantee 100% that you will receive the shortest path. Now, the way the heuristics work is it's adding 2 different distance values. Basically, that's what it's doing. So you add the distance from the start and the distance to the end. Now, I took that a step farther, and I added the distance from the parent's position, because we're traveling in a path. We don't really need to get the distance from the start. We just need to get the distance from the selected node. That will be explained in the video too. I'll do another 5x5 grid and show you that. Alright, so that's the second one. If it's not in the open list, we need to add it to the open list, calculate the heuristics, and then set the parent node to the current selected node. Remember, the selected node in this example right now is the start. We're looking at all the adjacent nodes at the start. Now, the last one is if it's already in the open list, we need to get a new distance from it. So if the new distance is, we get the current distance, the selected node. Remember, the selected node is the one we're looking at, and we're looking at all adjacent nodes of the selected node. So the selected node's distance from start plus the distance from the selected node to the adjacent node, that's the new distance. Now, if the new distance is less than the current distance, we update the distance and we set the parent is equal to the current selected node. That will be more obvious once we look at an example. Because we will visit several nodes, we might add a node here that we will not visit until at the very end, for example. And we might update the parent in that case. Alright, so that's the end of that loop. So that's what we do. We update the parents. That's basically the very basic idea behind this. So we need to gather the heuristics and update the parents based on that distance values. Now, once the parents are done, we're finished with the main loop. And now it either has the current selected node is the end, the open list is 0, or the end's parent is not null. So in either one of those cases, we're done with the while loop. So now we check to see if the end's.parent is not equal to null. So if the end has a parent, we're going to generate the path from start to end. Now the generate path is going to be basically reverse. We're going to start at the end and go backwards until it reaches the start. I know this might sound very complicated, but hopefully you will be able to understand it with the help of that video overlay again. Okay, so now let's walk you through the coding. So this is built on the Maps 2 tutorial, the Maps tutorial number 2, and I took out the player. There is no stick figure or anything, and I manipulated the coding and I changed some things around. For example, I added a tile class. Now the tile class has a display region and a tile type. Now a tile type in this example contains only two different values. It can either be passable or not passable. We either have a wall or we have we can pass through the selected node. Now the display regions are if it's passable, start, finish, not passable, in path, or closed. They're just useful for our eyes to see. Alright, so you can look at this. I just have a tile type, a display region, a map location, and point. So it'll be like 5,3, but it'll actually be like 45,630, for example. Also, we have an adjacency list that we need to generate. Now, this adjacency list is very easy to generate since we built the map in a multi-dimensional array. It is very easy to do, and I'll walk you through that in a little minute. Little bit. Alright, now we have our heuristic data, our distance from start and our distance to end, and our parent. And your heuristic is just one plus another. Alright, so our constructor, we have a point location. Every tile will have a point. We set it to passable. If we do not tell it a type, we set it to passable, and distance from start is 0. Now this is going to be my step further on the heuristics algorithm, and I'll explain why later on. Now we tell it a type, so we just set type is equal to type. Alright, add to adjacency list, we have tile t. If t is equal to null, we're going to return, because we cannot add a null to the list. Now, if adjacency list is equal to null, we need to create a new one and add it to it. ToString, I just did this for testing purposes, and it's just displaying the map location and the number of nodes in the adjacency list. Alright, so now let's look at the map class, the one we've looked at before. The dictionary is now changed from, char or something. Now it's display region, rectangle. We have a texture 2D background, content manager content. A char, we have an empty character, a start tile, finish tile, and not passable. Because our map is now going to look like this. That's basic. And it's going to look like this. A start tile is designated whatever we decide. I chose A. End tile, I chose B. Passable, I chose dash. And not passable, I chose the pound or number sign. So that's why we have the char there, so we can make it as abstract as we can. If you look at the Game 1 class, we pass it these values. So you can change them if you want to. Alright, Vector 2 map dimensions. We talked about that last time. Sprite font. That is for the time it takes. And this is in CPU ticks. So 5,308 ticks to do this map. However, let's look at the game1.cs and change this to the very first map. Look at the number of ticks, 4,524. So it's not that much difference. And there's the time again there. And tile dimensions, we have static tiles, so every tile is going to be the same dimensions. This used to be a char array, but now we set it as a tile array because we have our tile object built. Our tile sheet, our start point, our end point, and our path. Okay, the constructor is pretty much the same, just expanded on. We added the extra tiles, the end and the not passable char values. We set the display regions, we read the file, and then we generate the adjacency list. Load font, I generated that as well, just like the load tile sheet 1. Read file is about the same, except for it's going to call .region, and it's going to set its display region appropriately. So I just changed the values here. I created one for finished tile and not passable. And start was already there. And passable. So I just changed some things around. This looks pretty familiar to you if you've watched or looked at my maps tutorial or sample. Basically, I set if it's start, I set the start point to this. I initialize the tile ij to a new point, and then I set its display region. Okay, now to generate adjacency list 1. We need another for loop. We need 2 for loops, and then we need to loop through every tile and generate its adjacency list. Now, I'm allowing diagonals here. If you do not want to allow diagonals, you can just comment out a few lines here, and you're good to go. Now, like I said, it was very simple to do with multidimensional arrays. All I had to do was build another method here that says getTile, and I pass it if you look at a diagram, put a center point, build like a 3x3 a grid, and the center point is the one you're looking at, and you want to add the adjacency list for that center point. So we'll look at the one less column and one less row. Alright, so this just generates the adjacency list. Basically, it's a row, comma, column. So what I'm doing here is I'm saying the previous row and the previous column. This is up one and to the left. So it's a diagonal left adjacent node. One row minus and the same column. So that's the adjacent node just above that selected node. One row minus and the column to the right. It's a diagonal right one. Diagonal up and to the right node. And likewise for all this. I'm not going to walk you through all those. So these are using the getTile method. And the reason I built that is for ease of use. So I pass it a row and a column. And if the row is less than 0 or the row is greater than or equal to map dimensions.y, or the column is less than 0 or the column is greater than or equal to map dimensions.x, it is outside of our map, so we return null. Else we return the appropriate row and column tile. So basically this method is just saying if it's outside of our map, basically we're avoiding the array index out of bound error. Okay, once we do that, we get our adjacency list going. Now we can call AStar. And AStar will call AStar with start and end points, which is just the start location and end location. And I'm using a stopwatch. It's probably not the most efficient way to do that, but it only took me, 2 seconds? So, yeah. That's why I decided to use it. So, like I said, we need an open and closed list. And the open list must have something in it, otherwise we need to break out of the while loop. So here are my 3 terminating conditions that I mentioned before. While the selected item is not null, while the selected item is not the end, we continue our loop. While the open.count, while we have something in the open list, we continue our count. While the end's parent is equal to null, we continue the loop. So those are our 3 conditions, and at that point we find the best node from the open list. So we go back to the open list, find best node. The lowest node currently is going to be just the very first node in the open list. Tile N, the new open node. The new open node. And that will be the for loop. So that will be open sub I is equal to n. Now if n.heuristics is less than lowest.heuristics, remember we want to find the lowest heuristic value and store that in the lowest node. So if n's heuristic is lower than the lowest one, we obviously haven't found the lowest one yet, so we set the lowest one is equal to n. Else if. Now, here's another step further that I went than the actual algorithm used. I decided to, if we have 2 nodes, they have equal heuristics. Which one do we choose? Alright, the way I chose it was, these 2 have equal heuristics. Whichever one has the distance to end as shorter, the very first priority we decide is if it's closer to the distance, that one's the lowest. Now, if some weird situation is that both of those are equal, and lowest dot distance from start is greater than end dot distance from start, and basically here we're saying if the 2 heuristics are equal, we need to find out which one is closer to the end. If both of those are equal to the end, we need to find out which one is closer to the distance from start. Then, after all that for loops, we return the lowest value and we have our best node. Alright, if that best node is not equal to the end, we need to do our other stuff. So what I did here is I said, if that node is equal to the end, we will continue, which will break out of the while loop and generate its next iteration, which means it will never do this else, and it will just go ahead and go to the very top and check our logic here. So we already found the end, so if this hits, we will continue and it will say, oh, we achieved our result, we're done with the while loop. Okay, so now we're removing that selected node from the open list and adding that selected node to the closed list. Any node we get from the find best node method, any node we visit needs to be removed from the open list and added to the closed list. And for our visual representation, I'm setting its region to closed. Okay, so now we look at every adjacent node inside that node's adjacency list. And those are the three conditions I told you about before. If the adjacent type is equal to not passable, or it's already in the closed list, we do nothing to that adjacent node. If that adjacent node is not in the open list, we add it to the open list by calculating its heuristics and setting the parent to the current lowest best node. If it is already in the open list, we need to gather a new distance integer from the current lowest best node's distance from start and adding the distance from the current best lowest node to the adjacent node. Now, if that new distance is less than the current distance from start, our parent has changed and we have our new distance. Okay, so at the end of the while loop, if the end.parent is not equal to null, we have our path. So we generate the path and there we go. So right now, start was set to closed due to this. Remember, we add start to the open list, and there's only one list at the very beginning. So L will be the start for the very first loop through. So start is set to closed. So I just set it back to the display region as start. Now I'll stop the stopwatch and update its ticks. Okay, to generate the path, I mentioned this before, we go from the end and all the way back to the start by looking at their parents. So the tau P is equal to end.parent. While P is not equal to start, path.add, we're going to add the P, then we're going to set its region to in path. Then we're going to set P is equal to P.parent. So that's going to loop through until P is equal to start. Alright, so here's that add to open list where we do our calculations. Now, I mentioned before that I took it a step further. Instead of saying every node, heuristics, every node has a distance from start and a distance to end. Every node is going to use its distance from the previous parent's distance from start plus the distance squared of that node to the adjacent node. So we're actually, instead of doing the actual Euclidean distance from point A to point B, we're doing it from this path, from our travel point. Distance to end is the right distance squared adjacent node to end, and we add it to our node. Okay, so why am I doing distance squared? Euclidean distance is the change in x value squared plus the change in y value squared, all to the square root. Now, in programming or in computer world, a square root is very slow. So I'm just doing distance squared because I need to see if one's greater than the other. I do not need to have an exact distance. All I need to do is calculate if one distance is less than another distance. If I square root it, there's still going to be the same less than or greater than. So why not just leave it squared? It saves the computer some time. And AStar by itself is severely slow in the terms of computer sense. You saw I have like 3 different for loops and a while loop and all that stuff. And we're just using a 20 by 20 grid. What if you want to use a 500 by 500 grid? You're going to have to make some other adjustments as well. Alright, I think that's it for the algorithm. Everything else is the same. I basically just set child regions to the display region and we're good to go. So now if we look at the game1.cs, I generate a new level, a new map, and after all that's generated, I call map1.astar, and now we're good to go. Alright, I hope you got through that. It took me about a week in doing this and about 10 or 20 papers doing this on paper to work out. So if you have any questions at all, please let me know. I know it's probably very complex, but I like to help you through it. I'm at a limited time. I don't want to spend like a 5-hour video explaining it step by step by step. So some of you might get it. That's perfect. Some of you might not. That's okay too. Just ask me on YouTube or my website or email me or however you want to get into contact with me. If you're not sure about something, just let me know and I'll walk you through it. Alright, so enough talk. Let's look at the end result. So this is the baseline. Going from A to B, start to finish. A is start, B is finish. We need to get the shortest path from that. This is the very first map, very baseline. It's just a straight path right there. Now, I got rid of a few maps before. I didn't think those were... I don't want to demonstrate like 200 maps or anything, so I'll just demonstrate what I have right now, and you can add your own and try it. I've asked forums to see if they can generate a map and try to break it, try to make it less efficient and stuff like that. So let's go to game1.cs and set this to 10. Now map.10 looks like this. So it should be going here and down here. So now if we run it, remember the red nodes are the closed list. So they're there to indicate that we have visited that node, but it's not in the path. We have visited it, but it's not in the path. The path is the green, kind of green to brown gradient node. I thought that was a clever idea because the start node's green, the end node's brown. Why not make a transition from a green to brown gradient, and that will be a path. Alright, so you see it starts and then it travels back and then there we go. So that's the path. Now, like I said, I enabled to move diagonals. If you do not want to do that, you can just comment out the map.cs. Let's go back into the generate adjacency list. I think it's this one, these two are fine, this one, and this one. Yeah, see now I do not allow diagonals, so it needs to do something else to get the shortest path. which means it only can look at the up, down, left, and right nodes. Okay. Now let's look at one more map, and then we'll call this good. Map 11, which was somebody generated this map to try to confuse the program, but it did not work. Okay, so as you can see here, there is a lot of red on this area right here. Now hopefully my mouse is right there. For some reason when I record, I do not see my mouse on the game, but you see it in the video. So right here you should see some red. Now, because the reason you're seeing that much red is because it's trying to get the shortest path, which means it's basically following its rules. All this red down here is the shortest path to the end, but it got to the point where it's blocked off, so that's why it's red. And now we have our shortest path as going back to the left, then down, then to the right, and to the end. So it is following its rules and finding the shortest path, but it gets blocked, and then it goes back and goes to the other open list and all that stuff. So that is why sometimes AStar is so not very efficient that you should only do it if you absolutely need to. Now, in our tower defense tutorial, it is going to do it in the middle of the waves. It's probably going to lag a little bit between that, and we'll do like a sort of a message that says getting a star algorithm, and then once it's done finding that, it'll go away. But between the levels, that's what you'll get. Now, every time between the levels, no. Once you have a path, that's the path for good. When you put a tower that's in the path, then it gets a new AStar path. So I'm trying to kind of work around that and trying to see the point in the path. Okay, can I just +1 or -1? Can I get the adjacent node that's above it or below it? But I haven't gotten that far yet. So as of right now, if you place a tower on the path, it will have to generate an entire new path from start to finish. I'm trying to find a way to just find a path from the... actually, that might be a good idea. I'm going to need a doubly a parent and a child pointer if I do it that way, though. That's later on tutorial, so we'll get there. Alright, so this was a very lengthy tutorial. I hope you got the algorithm set. I talked about it 2 different ways. I hope the video helped you out a little bit. And remember, if you have any questions, it took me a week and a half to figure out what was going on. So, and 10 or 20 papers of doing it by hand. And I was tearing my hair out trying to find out what was going on. So, don't feel bad if you do not understand. I did not understand it until last week when I finished the sample. So, feel free to ask me, and hopefully my explanation was decent enough. I don't know. I'm trying to find out how much I should explain in these complex situations and how much is too much. So, if you have any questions, just let me know. Alright, so that's it for this tutorial. There will be no more tutorials until the Tower Defense series starts. We're done with the tutorials. I need to focus on finalizing the Tower Defense and debugging it and making it as efficient as possible, and then starting the series. So this is it for the tutorials for about 2 or 3 weeks. That will give me time to work on the Tower Defense, finalizing it, getting it ready to go, making sure it's all readable and I don't have 100 lines of code when I can do it in 10, all that stuff. Alright, so I hope you enjoyed this tutorial. This is officially a tower defense tutorial because we're going to use the exact same algorithm. Now we might change it some, but we're going to use the exact same algorithm. Alright, hope to see you in 2 or 3 weeks.